What's up, PreCalc? Here we are with 9.3 geometric sequences in series. We've learned that a sequence whose consecutive terms have a common difference is arithmetic. In this section, we'll study another important type of sequence called geometric. Consecutive terms of a geometric sequence have a common ratio. So it's going to be more of a multiplying, dividing type thing. So the second term divided by the first term would be the same number as the third divided by the second, would be the same as the fourth divided by the third, and so on. For each of the geometric sequences, find the common ratio. And again, they kind of give it away with the last thing here, but 3, 9, 27. These are all 3 to the n, so they're multiplying by 3s. 10, 20, 40, 80, 160. We're multiplying by 2 every time. Negative 1/4, positive 1/16, negative 1/64. So they are going by fourths and changing signs, so our rate is negative 1/4. All right. Finding the nth term. Our formula for the nth term of a geometric sequence is a sub n equals a1 times the rate to the n minus 1 power. Okay? And then kind of recursively, if you know the nth term, you can find the next term, the n plus 1th term, by just repeatedly multiplying by it. So there's our explicit, and then there's our recursion one. Write the first 5 terms of the geometric sequence. Whose first term is 2 and ratio is 4. So again, this is one that maybe you could just do off to the side. First one's 2 times 4 is 8, times 4 is 32, times 4 again is 128, and times 4 again is 512. So a small sequence like that might be a little easier just to manually do it and not have to do any formulas with that. Otherwise, you can sit here and multiply it all out. A1 equals 2. That was given. A2 is going to be 2 times 4. And then we have 8 times 4. (32 times 4). And 128 times 4 for 512. So a small one like that, you could probably just do it mentally without showing any work there. Find the 9th term of the geometric sequence, whose first term is 4 and the common ratio is a half. Okay? 9th term. So our A1 is 4, the R is a half. We're going to go up here and use this one. A sub n equals A1 times R to the n minus 1. So A sub 9 equals our first one, 4. That works. A9 equals 4 times, our ratio is a half, to the 9 minus 1 power, aka to the 8th power. And we'll probably type that in. Half to the 8th power, 1 over 256. Type that in, math frac, reduce. We got 1 over 64. All right, let's turn the page. Find the 12th term of the geometric sequence 5, 15, 45. Okay, well here's our A1, and we're multiplying by 3's, and we want to know A12. So that is going to be our first one, 5, times our rate, 3, to the 12 minus 1 power, aka the 11th power, $885,735. If you know any two terms of a geometric sequence, you can use that information to find the formula for the nth term. Okay, the second term of a sequence is negative 18, and the fifth term is 2/3. Find the sixth term. All right, so this one's going to be a little interesting. Okay, so A2 equals negative 18, and A5 is 2/3. So similar to what we would do with our arithmetic, but a little bit different. We've got to think a little bit more here. So A5, 2/3, would be how many times did you have to apply the rate to A2? Okay, these are 3 apart, so I would have to do the rate 3 times to get down to here. If you're thinking about it recursively, all right, I know this one. To get the next one, I'd have to multiply it by my R. That would get me to A3. Multiply it by R. Now that gets me to A4. Now multiply by R a third time, and I'm at A5. So A5 would equal A2 times the rate cubed, times the rate 3 times, R times R times R. So 2/3 equals negative 18 times R cubed. If we divide by negative 18, R cubed is going to reduce to, this is 2 over negative 54, so this is going to be negative 1 over 27. And if we cube root that, we should get negative 1/3 for our R. And now we can just take that R and apply it to A5. So if we take 2/3 times negative 1/3, negative 2/9. All right. The formula for the sum of a finite geometric sequence is as follows. Finite. Okay. So here they have the finite geometric sequence, A1 times R, A1 times R squared, A1 times R cubed, just keep multiplying by R each time. With the common ratio that R is not 1, because then you just have a big long list of the same number every time. The sum is A1 times 1 minus R to the n power over 1 minus R. Pretty crazy that that works, okay? Let's take a look. So we want the first 12 terms, 4 times 0.3 to the I minus 1. Okay? So if I put 1 in, 1 minus 1 is 0, 0.3 to the 0 is 1, 4 times 1 is 4. 4 is my first term. And then that, in the parentheses with the exponent on it, is my R. So A1 equals 4, R equals 0.3. We want to go up to 12, so we should have everything we need. So we're going to have 4 times 1 minus 0.3 to the 12th over 1 minus 0.3. How are we going to type that in? Very carefully. 4 times, let's see, if I was doing this, I would probably go super old school, double parentheses, 1 minus 0.3 to the 12th, close that, divided by parentheses 1 minus 0.3, close, close. Okay, if you have one of the newer calculators, you might do it like this. 4 times parentheses, fraction bar, and then just type them in the fraction bar. Ta-da! 5.17 or 5.714. Okay, the summation of terms of an infinite geometric sequence is called an infinite geometric series or simply a geometric series. The formula for the sum of a finite geometric sequence can, depending on the value of r, be extended to produce the sum for an infinite series. Because if you keep multiplying, well, we'll see it here in a minute. Specifically, if the common ratio has a property that the absolute value of r is less than 1. Okay, so if the absolute value of r is less than 1, the easiest one to think of is probably 0.5, a half, right? If you keep taking half to the exponents, that half keeps getting smaller and smaller and smaller. Half of a half of a half of a half. Okay, 0.5, 0.25, 0.125, it just keeps getting smaller until basically it becomes 0. Right? As n becomes really, really, really large, half to the 10,000th power is basically going to be 0. So we can then take that to be, right, as this goes to 0, 1 minus 0 on the top is 1, over just 1 minus r. So our infinite one is actually nicer than the finite one, but we have the catch that the r has to be, absolute value of r has to be less than 1. Then it's just a1 over 1 minus r. Piece of cake. Okay, so here's my a1. There's my r. It's clearly between, it's clearly absolute value is less than 1. It's 0.6 there. So we can use our formula for, well, we should write this down. A1 equals 4. R equals 0.6. So now we have 4 over 1 minus 0.6. 4 over 0.4 should be 10. Difference of a decimal place there. Ooh, they didn't give me the anything over here. My first term is 3. They didn't just give it to you, you have to think. Next is 0.3, 0.03, 0.003. We're multiplying by 1/10. And the absolute value of 1/10 is less than 1, so we can do this. So we have 3 over 1 minus 0.1. And we should be getting 3.3 repeating. 3 1/3. How do you want to write that? And banking. A deposit of $50 is made on the first day of each month into an account with 6% interest compounded monthly. What is the balance at the end of 12 years? This type of savings plan is called an increasing annuity. All right. So we have $50. Yeah, I don't think this is exactly the right one, but we'll go with it. This is a little bit old school here. No, this will work. Okay, so we have $50 times 5%, 6%. 6%. So we have 1.06. To the I power, and we're doing from 1 to 24, 2 years, 24 months. So we have 24 terms. Okay, so this is going to look like, let's see, 0.06 divided by 12. Is that 0.005? That's going to be the 0.005. And we're adding these up. We're adding these up. So it's not quite like the one from Algebra 2. So it's a summation. It's not just going to be this exponent one here. So we can kind of follow our summation formula. It's finite. So we're going to go back and try to apply this formula to it. So we have our A1. We have our 1 minus r to the n over 1 minus r. We're going to try to apply that formula to it. $50, and our very first $50 does get that interest, so we're going to put that right here. So that's like our first term, because that $50 gets interest for that first month. And then we have 1 minus the 1.0, if you put those together, 1.005 to the 24th power. Over 1 minus 0.005. So it's a little bit different than the Algebra 2 one. I'm going to go with my double. Well, we'll go with the more... No. Delete. We'll throw in the fraction bar there. And what do we get? $1,277.96. Okay, so our old formula from Algebra 2, principal times 1 plus r over n to the nt, is just if you put that 1 in and then let it go. So we had a little bit small difference here is that we're putting in a new $50 every month. And that's where we had to do our sum of the geometric sequence, because that first $50 gets 24 months of interest. That's why it's going to be this to the 24. And then the second $50 you put in only gets to 23, and so on and so forth. So that's why we're going to use our geometric sum formula for that, so it's a little bit different. All right, folks, there it is. Thanks for watching. Best of luck there. Take a look at some homework problems, and we'll see you next time.